as we've said, we start here at our starting materials point, and it's almost like in the It's almost like in the famous poem by Dr. Seuss, where let's see, can I read it to you? No. You're off to great places. Today is your day. Your mountain is waiting. So get on your way to react. You have brains in your head. You have feet in your shoes. You can steer yourself any direction you choose. So we're going to talk about what makes, but in this story, rather than trying to achieve, we are lazy, and we want to simply go over the most easy pathway. So our discussion from here on out in chapter 7 and 8 is going to focus on what makes the SN2 transition state higher or lower in energy. Similarly, what makes the E2 transition state higher or lower in energy. And then also what makes the SN1/E1 transition state higher or lower in energy. We've already solved that one because that one is our carbocationic intermediate, which I'm just going to label like this. And we already know what makes a carbocationic intermediate more or less stable. We're going to move that carbocationic intermediate down in energy as we go from a primary to a secondary to a tertiary carbocation. And we'll go in opposite direction for the rate. Okay, so the transition state A will similarly go higher in energy, lower in energy for more substituted carbocations, but faster in rate for more substituted carbocations. I'm worried that the two arrows are going to be confusing, so maybe we'll just do energy and then we'll put faster SN1 here /E1. Okay. So let's start with the SN2 transition state. We're going to see that the SN2 transition state goes down in energy if we have, relative to starting materials, if we have a good nucleophile. And maybe up at the top we'll put a weak nucleophile. I guess that makes sense. If you have a good nucleophile, then it should be easier to go to the right. Okay? And since going to the right initially is the thing that distinguishes SN2 from SN1/E1 and from E2, we're going to see that good nucleophiles promote the SN2 reaction. The other thing we're going to see in terms of the SN2 reaction is that because we have backside attacks, sterics is going to matter. So it's going to be easier to do the SN1 reaction for methyl and primary alkyl halides. It's going to be okay for secondary alkyl halides, but it's going to be prohibitively high for tertiary alkyl halides, simply because of sterics. So for tertiary alkyl halides, we're going to say too slow, no SN2. And the reason is, as you approach an alkyl halide from the backside, the alkyl groups on the tertiary alkyl halide will get in the way. Let me show you, looks like Adam's been playing on Mr. Beast. Okay. Wordscapes. All right, so we'll do this alkyl halide, T-butyl chloride, and there's the leaving group. I'm going to show you the HOMO and the LUMO. Dang it. no, I'll show you the LUMO. That's the sigma star. And notice that it's on the beta hydrogens. But let's put a space filling model on that. The blue lobe on the top here is where we need to attack the sigma star with the nucleophile so that the leaving group can leave. But now let's look at a space filling model, and you can see that little triangle in the middle, that's the carbon that has the leaving group on it, and you simply cannot get there, right? You want to form a new bond with that carbon in the middle, you can't get there, the methyl groups prevent it. Okay, so sterics sterics will prevent the SN2 reaction for tertiary alkyl halides, because that's simply going to move this transition state way higher in energy. Okay, so already let's look at a couple of offsetting ideas. We have carbocation stability, which affects these SN1, E1 initial transition state. And then we have alkyl halide substitution that affects the SN2 transition state. Notice that the SN1 reaction will be fastest for tertiary carbocations, which come from tertiary alkyl halides. So I'm going to write faster SN1E1 for tertiary alkyl halides. But notice that's exactly where SN2 is too slow. So that's a decision point that we're going to use if our starting material is a tertiary alkyl halide. We're going to know SN2 is not an option. And we're going to know SN1/E1 is potentially an option. But there's another part of the story, and that is that the E2 reaction is promoted by the energy of the E2 transition state is going to go down for a strong base. You can versus a weak base. Okay, so so that's why I'm saying that just because you have a tertiary alkyl halide doesn't mean you're going to go SN1E1 via the orange pathway, orange and blue pathways. You first have to deal with whether or not you have a strong base. So strong bases are going to make E2 reactions fast. So you can imagine a situation where you have a tertiary alkyl halide and a strong base. You can't do SN2, and you won't do SN1 or E1 because the strong base isn't going to wait around for the leaving group to leave. The E2 pathway is lowest in energy. Yeah?
How would you compare what you're defining as a weak nucleophile and a weak base and a strong base and a good nucleophile?
Good, great. How are we going to identify weak nucleophiles versus good nucleophiles, weak bases versus strong bases? Yeah, let's talk about that. Were there other questions? Go ahead.
My question is, why they switch from like the SN2 transition state, the tertiary? I guess why did the cation decrease energy when it becomes more stable?
Okay. Why does the carbocation decrease in energy when it becomes more substituted?
Yeah, as it gets more stable.
Stable means decreasing in energy. Stable means decreasing in energy.
Yeah, that's what I'm saying, but
Why?
Wouldn't the more unstable one be the easiest to get a reaction going because it doesn't want to be where it is?
So you're right that a less stable carbocation would be more reactive in the second step, but that's not the high energy step. The high energy slow step for SN1/E1 is this first one where leaving group leaves. And so, and the ability of the leaving group to leave is going to depend on how stable that carbocation is. because the transition state and the leaving group, the transition state and the carbocationic intermediate move in concert. They move together. So whatever stabilizes one stabilizes the other. You want a faster reaction, you want a lower energy transition state that leads to a lower energy carbocation. Because this first step is the rate determining step. The second step doesn't matter for rate because it's, yeah. Okay. All right. Whoa. Yeah, sorry, we're on the wrong, oh, that's fine. I feel like I've just had an out-of-body experience because I'm on the wrong page, but I thought I clicked on the right one. Oh, there's part 2. Okay. Whew. All right. Other questions you want to ask at this stage? I realize this is getting messy. And what we're going to do is distill all this down to a nice little table that if you don't want to ever see this free energy landscape again, you don't have to. You can just memorize the table. Yeah?
Small clarification. You said it chooses the E2 over the E1 SN1 because it doesn't wait for the leaving group to leave, it just attacks.
Right. If your base, if you have a really reactive base, what that means is the E2 transition state is lower in energy relative to the starting material. Really, when you have a reactive base or a reactive nucleophile, really, though I haven't said this, this increases the energy of the transition state. I'm sorry. If you have a reactive nucleophile or a reactive base, this actually increases the energy of the starting material, so you don't have as far to go to get over those pathways. Yeah. Okay. So the E2 pathway favored by a strong base. We'll talk about what makes a strong base strong versus what makes a good nucleophile a good nucleophile. It's sort of the same thing, but you can boil it down to a preference for attacking a hydrogen versus a carbon. And the other thing that's going to favor the E2 reaction is alkyl halide substitution. So we're going to see that the E2 reaction is fast for tertiary alkyl halides and is pretty slow for primary alkyl halides. And this has to do with the stability of the alkene of the pi bond that is forming in the E2 product. And we'll talk about that in greater detail. You don't need to worry about that too much. But this is what experiment has told us, that E2 is fast for a tertiary alkyl halide, whereas it's slow for a primary alkyl halide. Okay? So it's kind of different. It's sort of the opposite of SN2 in the sense that SN2 is fastest for the primary alkyl halide. Okay? So those are the major considerations. Now let's talk about each of these issues one by one and show some examples. So let's start by talking about good nucleophiles versus good bases. Good nucleophiles favor SN2. We'll put in parentheses if possible, because alkyl halide structure also matters. Good bases favor E2, and E2 is always possible, so we can sort of pause there. So I'm going to list some potential nucleophiles, and you're going to see that these are all conjugate bases of various acids, and I'm going to list them in order of pKa and a pKa of the conjugate acid, and hopefully I'm going to show you sort of where the dividing line is between nucleophiles and bases. So starting with sort of, I'm going to leave a couple of items. No. Yeah, I've got to leave a couple of items off the list because they're going to be sort of exceptions. So I minus, Br minus, Cl minus. We can look at their pKa's of the conjugate acid. HI is the conjugate acid, pKa is minus 11, minus 9, minus 7 for HCl. They are very stable on their own. These are weak bases, but they are still good nucleophiles. In part because they are large, and in part because they're negatively charged. This chapter 7 and 8 are actually about alkyl halides, so we're going to be using them as leaving groups. Good leaving groups are conjugate bases of strong acids. But later on, we'll have other starting materials where we might want to make an alkyl halide, and you can use these negatively charged groups as nucleophiles. Okay? On our list of things that could be potentially good nucleophiles would include the acetate anion, acetic or any carboxylate anion. Its conjugate acid is acetic acid whose pKa is about 4. And we're going to put here nucleophile / base. Let's continue going down the list. Let's see what's next. Thiols, thiolates, negatively charged sulfurs, are good nucleophiles. The pKa of its conjugate acid is around 8. Also on our list are some molecules you may not have encountered before. Azide anion is the conjugate base of some acid, I can't remember what it's called, pKa of 9. Cn minus is the conjugate acid of, or conjugate base of HCN, whose pKa is still 9. Those are good nucleophiles. We can put the amines on this list. So primary amines are sort of the best nucleophiles. We could also put ammonia here. Not the best of this list, but it turns out as you increase substitution on the amine, it gets more sterically hindered. The pKa of the conjugate, So the problem is that the pKa for ammonium, NH4, is a little bit lower than the pKa for a primary ammonium ion. So we'll just do this. Okay. And then I don't think there's anything else. If we get to the alkoxides and or hydroxide, by this I mean an alkyl group. R can be an alkyl group there. The conjugate base or the conjugate acid is water or an alcohol. From this point on, we're going to say strong base, but good nucleophile and good nucleophile. Okay. So, and they're listed in order of, roughly in order of strength, though there's some weirdness in there that we don't need to talk about. But the cutoff between a weak base and a strong base is going to be conjugate acid with a pKa of about 16. This is where things start being good bases. So you see that it's you can attack carbon with something that's fairly far down on the list in terms of pKa reactivity, but you can't attack hydrogen with generally, in the starting alkyl halide material, you can't attack it with a weak base. So this is where, when you're using a nucleophile whose pKa is 16, whose conjugate acid has a pKa of 16 or above, that's where you start worrying about strong base. Okay? Let's see. So we could put some other things on this list. I'm trying to think of the one that maybe would matter the most would be acetylide anions. This is going to be one of our only carbon-carbon bond-forming reactions in 351. The alkyne proton is more acidic than your typical CH bond because the sp hybridized carbon is more electronegative than an sp3 carbon, and so the conjugate base is more stable. These are going to be both strong bases and good nucleophiles. Okay, so yeah, I guess the arrow's fine. Questions about that? Yeah.
So are all of those that you listed good nucleophiles? Does the arrow indicate that it's like increasing?
They are all good nucleophiles. The arrow sort of indicates that they're increasing in reactivity, though there's an asterisk on that because the size of the nucleophile matters and also the solvent matters, though your text delves into that, and I really just don't care about that at this stage, so we're not going to worry about that. Yeah. In reality, iodide is a great nucleophile, and so is the thiol, even though they're not this far down on the list, and it has to do with their size and something called polarizability, but that won't be important. As long as you remember it's on the list, that's good enough. Okay? Other questions? Yes?
So the ones at sort of 16 will attack the hydrogen?
The ones below 16 can attack both the hydrogen and the carbon. So the ones up here, in terms of, the ones up here will prefer SN2 if possible. The ones down here will have the tendency to do both, depending on the alkyl halide structure. All right, so okay. Okay, well, so far we've got some examples of weak bases, but we don't, oh yeah, go ahead.
I was just going to ask, why are strong bases, I guess, more favorable to an E2 reaction? Because, bases want, like, protons, right?
Yeah.
So, I guess, why would a strong base that wants a proton be, like, it's easier for its proton, one of its protons to be taken?
Yeah, that's a good question. I mean, really, the reason we know it's a strong base is really, I mean, pKa data comes from like proton transfer reactions where you're swapping proton from one acid to a base. We don't have a pKa scale so much for nucleophiles. There is such a thing, but it's complicated enough that we won't talk about it. What makes a good nucleophile good? There's actually two ways to be a good nucleophile, and this is something called hard soft acid base theory. But you can be a good nucleophile by having high energy lone pair as the HOMO, and that would be things like hydroxide or further on. The other way you can be a good nucleophile is to be large. Well, I want to be careful about large. To have shoot.
You don't have to go into it.
High polarizability. So to briefly summarize, iodide, its valence electrons are held far from the nucleus. So if I'm drawing the electron cloud of iodide, it is very easy for iodide, and the I represents the position of the iodide nucleus. It is very easy for iodide to distort its electron density to one side, and that's useful in approaching some alkyl halide where you've got a leaving group here, because then the iodide can distort its electron density more easily such that it can get in close to where the leaving group is, and the leaving group leaves easier. Larger things, larger atoms like sulfur and iodide and bromide tend to be more polarizable than something like oxygen. Oxygen's small, its electrons are held pretty tightly and in a very small space, so it's not very polarizable. And that's sort of the difference. And so I won't make a big deal out of this, but this is the reason behind why a lot of these are good nucleophiles, even though they're not good bases. Because you can be a good nucleophile by being a good base, but there's this alternative pathway available too. Yeah. All right, what else? So, exceptions. Those are always fun. We haven't seen any weak nucleophiles yet. The following molecules are going to be in the category of weak nucleophiles / and weak bases. And these are going to be the reactions that aren't going to do nucleophiles / bases that aren't going to do SN2 and are not going to do E2 because they're not reactive enough. So these include water and alcohols like methanol or ethanol or some other alcohol. Okay, in general, alcohols. Neutral water, neutral alcohols, these are both weak nucleophiles and weak bases. The reason I didn't put them on the list is because the pKa of their conjugate acid is -2, so they show up right here. And you'd ask, well, how can the halides be good nucleophiles but water isn't? And again, it's this weird issue of polarizability. Yeah?
So when you say not reactive enough, does it mean it's just slower, so it has to go?
Yeah, they're not reactive enough. For these molecules, the barriers to SN2 and E2 are so high that the only alternative is to wait around for the leaving group to leave to get a carbocation, and then you're going to get both SN1 and E1 products. Okay, so these are going to, your text says favor SN1 / E1. It's not so much an issue of favoring as it is an issue of there's simply no other options. And often these types of reactions are, in the nucleophile that we use is in many cases also the solvent. So these reactions are sometimes called solvolysis reactions because an example of that is this tertiary alkyl halide. It's not going to do SN2 because of sterics. And we're going to use methanol as our solvent. Because we have a weak nucleophile / weak base, there's going to be no SN2 and no E2. Even though E2 would be okay for a tertiary alkyl halide, your nucleophile isn't / base is not reactive enough to do it. So we have to wait around for the leaving group to leave. We get the carbocationic intermediate, and then one of two things can occur. The weak nucleophile and weak base, and now that it has a super reactive intermediate to deal with, the nucleophile can attack the carbocation. If the nucleophile is water or an alcohol, that leads to this positively charged oxonium ion intermediate, and then usually another molecule of your alcohol from the solvent removes that proton to give you the neutral substitution product. if this were a stereocenter, we get both varieties. Methanol is also not a good base, but the carbocation is reactive enough that because of sigma to P hyperconjugation, the beta proton becomes very electron poor such that it's acidic enough for methanol to remove, and then we can get the elimination product as well. So we see SN1 and E1 products for that particular combination. Okay, so what we're saying for that scenario is that the transition states for SN2 and E2 are simply so high for those nucleophiles and bases that the only thing they can do is wait for the leaving group to leave. You get to the carbocationic intermediate, and there it's anybody's guess as to which pathway is more favorable, whether it's the SN substitution pathway or the elimination pathway. And so you get both substitution and elimination products there. Yeah?
Is it like a 50-50 chance? Or?
Is it 50-50? It varies case by case basis. So I'm not going to ask you ever to predict which substitution versus elimination product, which of them dominates. I'm going to have you anticipate both options. Okay? The reason I'm going to do that is we're going to see as the class goes on that there are other things that can happen to carbocationic intermediates, and you will, like there's other pathways branching off this. You're going to conclude that if you can avoid it, you should avoid a carbocationic intermediate. SN1 and E1 reactions are cruddy in terms of yield and in terms of selectivity. If you start a reaction and you want one product and you get a mixture of products, probably that's not a great way to go. I'm showing you it mostly as a way to talk about competing reactions and also as a way to talk about carbocations. In general, this is not synthetically useful because, yeah, it's anybody's guess as to what you're going to get as products here. There's even more options, actually, than I'm showing you here because of a little something that I won't tell you about now, but which is called carbocation rearrangement. Okay? And it's okay if the SpongeBobs are running around on fire in your brains right now because it's not a particularly fun topic. Okay. Let me show you. Any other questions on that? Yeah.
ME stands for methyl.
ME stands for methyl, yeah.
And that was, you just showed the SN1 versus the E1 reaction in that drawing.
That's right. And the ME there represents methyl group. And we're going to get both substitution and elimination products there. Yeah, I'm sorry about that abbreviation. O-chemists do that all the time just because writing out CH3 is a little bit slower than writing out ME. Okay, others? All right, let me give you another scenario. Do I dare? Do it. Yes, I do. Okay. So I'm going to use as my nucleophile sodium ethoxide. You buy this in a bottle and it's labeled NaOET, and the solvent is ethanol, though that doesn't matter. ET stands for ethyl group. And sodium is the counter ion, which we are going to ignore. It turns out that counter ion can have an effect on reactions, and that's especially true in 352, but we're basically not going to care about it. So if I write this in a reaction, you need to practice enough so that you look at this NaOET and you see that in your mind, or you can draw it on your paper. You need to learn to ignore the sodium and remember that this is an alkoxide nucleophile / base. and it is a good nucleophile, and it is also a good base. Okay? So automatically, we know if it's both a good nucleophile and a good base, we know we're not going to wait around for the leaving group to leave. Because depending on the situation, either substitution or elimination or both will be options to this good nucleophile or base. Now, we have a secondary alkyl halide. What we said for secondary alkyl halides in terms of rate was it's sort of intermediate for E2 and also sort of intermediate for SN2. So we expect both SN2 and E2 to be possible for this alkyl halide. So you have both SN2 and E2 possible for the good nucleophile and the good base. You have the same thing possible for the alkyl halide. So we need to draw both SN2 and E2 products. The SN2 product would look like this. It would be backside attack of the ethoxide nucleophile. And then to determine the E2 products, we need to first identify all the different beta protons. Here's one in purple. Here's one in orange. If I remove the purple beta proton, kick electrons down and the leaving group leaves, that will give me the purple elimination product, which is here. If I remove the orange beta proton, I have, let's see, orange beta proton with my base. I will make either of these two alkenes. I will make either the cis, the trans or the cis. Now, in the case of elimination products, when multiple elimination products are available, the most stable alkene wins. And we're going to talk about alkene stability, but let's just put a pin in that for right now. So you see that because we had a good nucleophile and a good base, SN2 and E2 were open to us. And because we dealt with a secondary alkyl halide where the rates are just sort of intermediate for both SN2 and E2, we expect both possible outcomes. Okay. All right. Other questions? Yeah.
Just a clarification. So say it was a primary nucleophile attacking it, we would expect it to be primarily SN2 and not really E2?
Sure. So let's deal with this situation where we have a primary leaving group, right? Primary alkyl halide. And then let's change it up. Let's use something like the acetylide anion, which is, based on our discussion above, both a good nucleophile and a good or strong base. I can't decide whether I'm going to say good or strong, same thing. Okay, but if we go back, so we might expect SN2 and E2 products from the base / nucleophile. But if we go back up to our diagram and look at how alkyl halide structure influences the E2 versus SN2 reactions, we said the SN2 reaction is fast, wicked fast for the methyl or primary alkyl halides, and it's slow for E2. Okay? So what that's going to tell us is even though our base could potentially do E2, SN2 is so fast and E2 is so slow, meaning that SN2 barrier is way lower than the E2 barrier. So you're just going to get SN2 products only. So the product there, nucleophile attacks alkyl halide from the backside at the sigma star. We make a new carbon-carbon bond between the carbon that had the leaving group and the, and the sp hybridized carbon, negatively charged carbon of our acetylide anion. And so I started with 1, 2, 3 carbons. I end up with 1, 2, 3, 4, and 5. That is we just sort of want to pause and celebrate because that is maybe our first or second sort of real carbon-carbon bond forming reaction. You could argue that when we did cyanide as the nucleophile, that was also a carbon-carbon bond forming reaction. But there's less stuff you can do with cyanide than you can do with carbon-carbon triple bond. So, yay, and there was much rejoicing, right? Yay. Yes?
So I'm trying to simplify it so I understand it. The way this would not work for E2 is because where the bromine is, there are not as many beta protons.
Yeah, you can think of it that way. Why is E2 slower for the primary alkyl halide? Yes, it is because there are fewer beta protons to be removed. It also has to do with the stability of the E2 transition state. The E2 transition state has a significant amount of carbon-carbon pi bond formation in it. And we're going to see that more substituted alkenes are more stable, and that'll be true for the E2 transition state as well. And if we have more things coming off this carbon, if we made a secondary carbon or even a tertiary carbon, the alkenes we're going to get are going to be more substituted and more stable, and therefore the E2 reaction is going to be faster. Now, that's looking ahead because we haven't talked in a lot of detail about alkene stability. So yes, it does have to do with statistics, the fact that there's just fewer beta protons, but it is also an issue of the stability of the alkene that's forming. All right. So this was, let's see, what have we seen so far? We did a weak nucleophile / weak base. We did a strong nucleophile / strong base where we got a mixture of SN2 and E2. We did a strong nucleophile strong base where we only saw SN2 because of this difference in rate. There's other combinations we could look at. For example, we could take this tertiary alkyl halide and say something that is a good nucleophile and a good base. So you would expect SN2 and E2, but you have a tertiary alkyl halide for which SN2 is just basically infinitely slow, whereas E2 is fast. So we're only going to see E2 products only. Even though we've got a good nucleophile, we're going to see just the elimination product because the nucleophile can't get to the sigma star on the backside of the carbon-bromine bond. So elimination is all you can do there. Yeah?
Wouldn't that be considered like an alcohol group? So would that be like SN1?
Would this be an alcohol group? No, this is an alkoxide. It is the conjugate base of an alcohol. The alcohol and water are weak nucleophiles. Their conjugate acids are hydronium and the protonated alcohol. So that may be with the pK of -2. So that may be the source of the confusion. There's a difference between the alkoxide, which is negatively charged and is a good nucleophile, versus water or alcohol, which are neutral and not good bases or nucleophiles. Okay, others? Yeah.
If you back out
Sorry. Scroll.
Yeah, that one. The chemical below the arrow. What does that mean?
I'm just writing. So there is no meaning intended to be communicated by above or below the arrow. I was just writing what somebody might put instead of writing out the reagent this way. I wrote it this way so you could see clearly what the nucleophile is, but you need to get used to thinking this when you see this. Okay, what else? So based on what we've talked about today, we have the beginnings of sort of a decision tree where we can split across the top. We can draw things that are good nucleophiles and good bases. We can draw things that are weak nucleophiles / bases. We have seen things that are good nucleophiles but weak bases. I'm going to show you later, we haven't seen this before yet, a strong base that is nevertheless a weak nucleophile. And then we're going to interface that with alkyl halide structure, primary, secondary, and tertiary. And you can create a little table here, and based on the considerations we've talked about, and we'll finish up next time, you can predict what happens in each of these situations. And that's all of the situations you will encounter in chapter 7 and 8. All right. Go forth to learn.